Hello everyone, good morning, good afternoon, and good evening. I am Asma Shindi, petroleum engineer graduated from American University of Ras Al Khaimah, and I will be your moderator for today. On behalf of BioPetro, Arab Oil and Gas Academy, and SPE Egypt section, I would like to welcome all of you to the third lecture of our short course, Effective Python Programming for Exploration and Production. Also, this lecture is part of our natural gas engineering internship. The lecture is presented by a special speaker, engineer Yohanes Nuwara. Before I present our speaker, I would like to remind you if you have any questions, please drop them in the Q&A box and keep the chat box professional. Now, our speaker is Yohanes Nuwara is now working as a distributed acoustic sensing geophysics in the Wright Institute, Kyoto, Japan. He holds a bachelor in geophysics. He had achieved outstanding achievements in many places. One of them was minus CO2 challenge by Equinor and EAGE in 2018. He had several high-ranked publications. One of them is about integration of rock physics, time-lapse seismic modeling, and geomechanics for CO2 storage, in which he will present in the 82nd EAGE annual conference this October in Amsterdam and Netherlands. He had been working on open source Python programs for geoscience and petroleum engineering since 2020 and had been teaching to more than 1,000 SPE students and professionals worldwide. In his free time, he loves writing blogs and towards data science medium publication involved in his Python for geoengineers community in Telegram, reading biography books and doing sport. So pay attention and welcome Engineer Yohanes Nuwara. Engineer Yohanes, the mic is yours.
Thank you, Asma, for your introduction. And hello, everyone. It's been a good day. Um, so today we are going to discuss another new topic. It's called the exploration data analysis. I hope you enjoyed being in the previous two courses on the basics of Python programming and the production data analysis. If you just join in this session or this lecture, I recommend you to watch the recording in the YouTube so you can just follow all of the discussions and the source codes that we just go through. And actually, I have the links to the source codes that I just shared to you in my previous sessions. The first session is about basics of Python, and the second session about production data analysis. If you are interested and you are curious enough to try all of those source codes, here you can access the source codes. And one thing I would like to point is that if you want to learn Python, you have to practice. If you don't practice at all using the source codes, or you just leave after sessions, you won't learn something because to learn programming, it requires a constant practice. And how to start your practice, you can follow the codes. And then if you just finish running all, you have to try analyze what you can add to the source codes, how I can improve in my source code, and how to make things out from the source code, and how to make any other things. Just be creative. So here you can access the links. After the session, I will again share the link, and the format is actually the same. PyoPetro source code 3 for this third session. You can access it once we finish our session today. Okay, so we are just going through directly to the Google Colab because we are using Google Colab in our previous sessions. Here I have prepared the notebook for you, and we will code from scratch. Okay, and after the session, I will share this notebook to you, the links, so you can also run the codes and learn one by one. Okay. And today we are going to talk about exploration data analysis, exploration data visualization. Okay, you have been already known about exploration data. what types of exploration data that you will come across. For example, Veloc data for formation evaluation. And probably if you are a geophysicist, you may be handling with seismic data, 3D seismic data. That's an exploration. And also some data that you can visualize the trajectory of the wellbore and the fracture data or image data, core data, and the data about the lithology that you obtain it from the mud logging operation. It's all in the exploration stage. And today we are going to visualize some of this data that is categorized in this exploration stage, which is the Veloc data and the trajectory data and natural fracture data. Okay, this will be going to be interesting because this is a new topic that I haven't covered in my previous courses last year. And the new topic is the natural fracture analysis. You can implement this source code if you are working in hydraulic fracturing. You are processing natural fractures data. You can use this code to visualize your data. Okay. Two libraries that I want to use right now is the LACIO and MPL Stereonet. If you still remember what we have going through in the last session, we have discussed about the use of Seaborn and Plotly, I guess. It's to visualize the production data. And today, LACIO and MPL Stereonet are two libraries that you can use to LACIO is for Veloc data, and MPL Stereonet for natural fracture data. Okay. Again, the first thing when you start your notebook or your Python code, you just import all of this library. But because LACIO and MPL Stereonet is not already available in Google Colab, you have to install it first. Okay. So the way you are doing the installing of these two libraries, you just type pip.install LACIO and another one for the MPL Stereonet. Okay. And then you just run this code and it will install these libraries into your notebook. Okay. Why we don't install NumPy, Matplotlib, Pandas, Seaborn, Plotly? Because most of the libraries have been already installed in Google Colab. But some libraries, for example, the libraries for our specific things, you have to install it first. Okay. But because you are working in Google Colab, you don't have to install these libraries into your computer. You just install this library without downloading it, just by doing the pip install LACIO, and then you will get the libraries in your Google Colab without you have to download this library. Okay. And then I will add another library I have prepared for you. This library I will use for visualizing natural fracture data. Okay. So here, this is the URL or the web link to access my library. The library is called Fracture. Okay. And I would like to get this library into my Google Colab. Okay. So I can run this. And you will see that this library has been already in this panel. Okay. If you double click this, you will see the functions. There are two functions in this program. It's called the Stereonet and the rows diagram. Okay. So this one we'll use for visualizing the natural fracture data. Yeah. And then we just go through our usual routine. We import the NumPy, Matplotlib, and Pandas. Oops. The second one is Pandas. Okay. And then the additional libraries because we have already installed these two libraries, we are going to import this. Okay, import Lazio and import MPL Stereonet. Okay, and then we also import the library that we have already accessed here. The program is called Fracture. So we are importing the Fracture program. Okay. All right. So after we have done importing, we have here the data. Okay. Yesterday we are talking about production data, but today we are going to talk three data, which is the wireline, well logging, and the trajectory and the fracture data. And you can open this. You can copy this and open in your browser, and you will see the data. This is the data. So this is the wireline Veloc data. You can see it. This is the last data. Maybe you haven't already seen this data before. So this is the Veloc data that petrophysicists are working with every day. In petrophysical softwares, they require a certain format that is called a LAS data. So there are lots of formats, for example, CSV, Excel, and the petrophysicists, they have their own special format that is called the LAS. So that's why we are calling our library this LASio, because LAS, it stands for LAS. LAS is the format, and IO stands for input and output. Okay, and then this is the trajectory data. You can also click this link, fracture data. You will see the data. But now I want to skip seeing the data, because you can do it yourself. We just run this data, and after running this data, you will get this data into your system. Okay. So we are going to the first section. We will visualize the Veloc data. Okay. Actually, there are many courses on how to visualize Veloc data. They are everywhere. Whenever you are browsing in the internet, you will see how to visualize Veloc data, because visualizing Veloc data is really important, and it is really simple. So maybe I will start by discussing about this topic, although you can develop it further after you finish this course, because there are lots of courses there, articles in Medium. You can start reading how to play with Veloc data in Python. Okay, so the first thing, we are going to read our last data. Okay, so we use the Lazio library, and we use this Lazio.read. We use the read function from the Lazio library. Okay, and we type the path to our data, because here we have already defined the link here. It's called the well path. Okay, the well path, and if you run this, it will read the data into Google Colab. Okay, Lazio read.wellpath. Okay, so I forgot to type a new variable for this. Maybe well df, because sorry, it's well. It's okay. So well equals Lazio.read. Okay, and then one more important thing when you start working with LAS data, you have to look at the header of the file. Okay, so for example, here I show again our data. This is our header here. Okay, and this is our content, and each of this column is related to this description. For example, the first column is depth, and the second column is the lithology, caliper, density correction, DRHO, and this one is the neutron porosity. I guess you have already understand this. And Roby is the density, gamma ray, And DTC is a compressional def time. It's a sonic lock. And this one is the elastic. So this is the VP. If we invert DTC, we'll have a VP. And if we invert DTE, we'll have a VS. And this one is the deep resistivity, spontaneous potential, and this is the resistivity, okay? And we are going to find out, assuming we cannot see the data, okay? If we cannot see the data, we can display all the information in Python, okay? The way we are doing this, we just type well.curves, and it will print us all the information in our data. Here, you have the depth, lithology, caliper, all the logs that are present in this data, okay? So this is called the mnemonics. Mnemonics are all the information in Veloc, what logs we have in our data, okay? And it's you can also see what units, what are the units that they have here. The density, they have a gram per liter, and all the units you can see. And then this one is the shape of the data. It's not too important, but you have to see this, the depth and the meter, okay? And then actually, the data is in form of NumPy data, okay? It's a form of array. So if we print the data, well, the data, you will see all the information, all the values are in NumPy. If we are seeing this, it is quite not comfortable to see our data in this format. We always want to see the data into a CSV or Excel or spreadsheet data. So that's why we can convert this data into a data frame. So don't forget, we have already discussed about how to make a data frame, how to convert, and how to read a spreadsheet in our production data analysis. We have already talked on how to convert into a data frame. So here we again convert this data into a data frame so that we can display it as a table, okay? So there is a question, can we use pip install for the user-defined library fracture? That's a good question, thank you. Actually, if you want to use the pip install thing, if you go to this website, pyp.org, pyp.org is a website where all developers are putting their libraries into this pyp.org. So if the developer or any library has been already featured in this website, you can do the pip install in this notebook. But because I haven't uploaded my program here into PyP, we cannot do so. So we can just import this library using widget. Actually, this library is contained in my GitHub. Maybe some of you followed my GitHub already. So I have a GitHub, and in this GitHub, you can see all of my libraries here. It is a quite complete documentation of my repositories, and you can go here, my GitHub and formation evaluation. Actually, the library is inside this repository. Okay, so this repository contains all functions you can use for Veloc analysis, and this is my function here. So from this link, okay, so from this link I access it directly to Google Colab. I hope you understand this, because some people prefer to use GitHub to store all the libraries, and I have my own GitHub to store my lots of libraries here, not only formation evaluation, but if you are also interested in reservoir engineering, I also have them, the libraries. Maybe in the later session after this discussion, we can discuss it more. Okay, so we back to our previous discussion here. We want to convert the well data to a data frame. Okay, and how to convert this? We have already defined our data. It's called the well data. Okay, and then we use it well dot to df. Sorry, it's well df. Okay, okay, but you have to add this reset index. Okay, so after this, you have already done converting all the data into a data frame, and you can see the data in a form of spreadsheet here, okay? And it's more comfortable to see this data right into this form. So we'll use this format to through our analysis here, okay? So this is the I hope you still remember our previous discussion. These are our features, okay? Columns are features, and there are 21,000 observations or rows in our data. Okay. And the fun thing here, I would like to share how to visualize this data, because the core activity in every petrophysics or formation evaluation activity is how to visualize this data. Okay. So before we are going to our part, let me share to you how you have to learn the basics of for looping, because in the previous discussions we have already discussed about this for looping. So actually, for example, we have a list of names here. List of name. For example, John, Matthew, James, Peter, and Andrew. That's the name of apostles. And again, so in this code, I would like to print each of these names, okay? So John, Matthew, James, Peter, Andrew. I would like to print all of the names. So I use the for looping to print one by one, okay? So you just type for I in, okay. So there are two ways to do this. This is the first way, okay? It is quite important for you to learn the basics of programming, because for looping is actually the basic of all programming. If you learn not only Python but MATLAB, C++, or R, Java, Julia, they will start the discussions from array, for loop, if conditionals, and all of those things. So you have to master these things, okay? So a concept that is called the for looping. So we can use the for I in list name, okay? And then print I, and it will print the name one by one here, okay? John, Matthew, James, Peter, Andrew, okay? There is another way to do this. For example, here for I in, we use range len list name. Okay, maybe for some of you, it's still you're still wondering what is the meaning of this code. So let me show to you first. If you want to print the length of an array, you can use this length of len list name. So okay, so the length is 5. There are 5 names here. Okay, so for I in range, okay, what is the meaning of range? Range will loop all of this name 5 times, okay, because the length of the array is 5. So it will loop this name 5 times, okay? And if we print the list name I within index of I, you will come up with the same result here, okay? So, okay, I have to remind to all of you, because there is a certain convention in Python. If you want to print the first value in an array, you can call this maybe list name 0. Okay, so list name 0 is the first value in the array, and the last array is the -1. So -1 is Andrew. Actually, if you are learning MATLAB, the first index is not 0, but 1. But for Python, all index starts from 0. So 0, 1, 2, 3, 4. So the last array is 4. Okay. And then um, I'm going to discuss about the if conditional or for looping. Okay. And then so here I would like to do something like like to check which name is not James. Okay, so John. So if John is not James, Matthew is not James, but James is James. So I would like to check whether a name is a name. Okay, so we use another concept here. It's called the if conditional. It's also the basic thing in programming. Okay, so we can combine this for I in range for the length of list name. Okay, and then for this, if list name is James, okay, so if the name is James, so I will print his name is James. Okay, but if not, so I print else. If not James, so I will print his name is not James. So you will guess in this array which name will print his name is James and which one will print his name is not James. Okay, so if we run this, you will see, okay, it's correct here. So John, his name is not James. His name is not James. For James, it's James, not James, not James. So this I combine if and for looping. So this is the conditional. So if you want to give an exception, you have to start by using the conditionals. Okay, so I started from this very basic concept. I would like to visualize the data using this concept. Okay, why I would like to I start from this thing. Look, we in this data we have a resistivity data. Okay, this resistivity data, for many petrophysicists, they prefer to plot the resistivity data into a form of logarithmic plot. Okay, so for example, I would like to maybe resistivity logging, resistivity log data. Okay, so maybe I will share you one picture of resistivity data that have this one. Okay, so if you see this log, okay, maybe this one. If you see this log, the resistivity data, it is plotted not into a normal plot, but it is in resistivity. It's in logarithmic plot. So for this data, I would like to give an exception for this. For this resistivity data, I would like to plot in a semi-log or semi-logarithmic plot. But for other data, it's only the normal plot. Okay, so I will show you because it's quite maybe some of you don't understand already. So this we first to visualize, as usual, we use figure. And then PLT show. Okay, so I would like to make a subplot of this data. Okay, so I would like to show the data, just 5 data: the neutron density, gamma ray, resistivity, and the compressional sonic log. Okay, and I would like to make subplots of plots. Okay, if you still remember our previous session, we have been talking about how to make a subplots visualization using matplotlib. But instead of doing like this, plt.subplot all the times, okay? So for this 5, so plt subplot 5, 2, and etc. until plt dot subplot 5, 5, okay? So instead of doing this, we can use the for looping to automate our data. So because our topic here is effective Python programming, so I think it's a nudge for me to share how you can effectively programming. Instead of using this, you can use the for looping to do things much more simpler. Okay, so for I in range len well, okay. Okay, so so there are 5 flocks here. So this is 5. Okay. Okay, so maybe I just skipped another step here. First, um, I would like to define which column I would like to show. Okay, so lock is NPHI, gamma ray, resistivity, and DTC. Okay, so for I in range log, okay, print well dot log dot I. Okay, so basically, I would like to show the information in each. So how can I say? I would like to show one by one inside a list of names. Okay, so well log well dot nphi. Okay, I hope you understand this. Okay, so this one well and nphi, it will print all the neutron data. Okay, and then we have already defined our log. So here in a range of 5, because we have 5 logs. Okay, we use the plt.subplot 5 I plus 1, and then plt dot plot. Okay, because for this is the resistivity data. As I said before, I would like to show this resistivity data into a semi-log plot instead of normal plot. So I give an exception here. If so if log I equals resistivity, so we plot in semi-log. Okay, so the way we are plotting the semi-log, we use semi-log x, and because we want to visualize the x-axis as our data and the y-axis is our depth. Okay, so the x-axis, you define it first as the well log I, and this one, the y-axis is depth. Okay, and then for the other data, this data and this data, we just plot in normal. Okay, so PLT plot Veloc I and well the depth. Okay, depth. Yeah. So if we run this code, you will see the data. Okay, all the data. Okay, and then you can see that it's not quite a nice look of our data. I would like to give a distance between one plot and another. So we use this to make a distance, and I can use I can change the size 7 9. Okay, so these are our logs. Okay, perfect. And one thing you have to concern is that the depth is still, you have to make it from the shallower depth to the deeper depth. So this one should be on top of here, okay? So you have to reverse the y-axis. How I reverse the y-axis? Well, you can make a limit to your axis, the y-axis, and the axis is for example, from this 300 and 3001 and 3500 and 1000. So you place it here. It will give you an inverted depth. Okay, and then I would like to make a grid to make it more perfect here. Okay, this is the grid, and if you want to plot in different colors, you can define first the list of colors. For example, the first one is black, red, green, purple, and blue. Okay, so here, okay, so if you type, for example, red and color equals red, okay, it will give you all the plots showing in red. Okay, but you want to define each data into different color. So instead of using red here, you again using the concept of for looping. Okay, so color equals color because we have already had the list of colors. So color I, and this one is color I. Okay, so it will print us the logs in a different color. And then I would like to give a title, and the title is different for each log. And again, we are using the same for looping. So we define it as, because for the first column, I would like to plot MPHI, etc. So the same syntax here, the PLT, sorry, it's no, PLT the title, this one. Okay. All right, it's perfect. Okay, I think I would like to go to the chat feature. Okay. Okay, so for this Veloc visualization, we have already covered on how to plot this log. Okay, and see here the resistivity is already in a semi-log plot. Okay, so okay, okay, so this HOB. Okay, we have already visualized our data. Okay, and then the second thing is the well-bore trajectory. Okay, here I have already had the data here. The data is from this one, the trajectory path. If you're going to this link, you will see the data. So this is the data, okay? This is the data of the trajectory, the well trajectory, okay? So using the data, I would like to visualize a trajectory, okay? Because this is the CSV file, so we use pandas, not Lazio, to visualize this, okay? So remember, we use what function we use for reading a CSV file. We use a panda.read CSV, okay? So we define first as trajectory df, and then panda read CSV, trajectory path, okay? And then if you um, visualize the data, okay, this is the data maybe for the 10 first rows, use hat, okay? So this is our data. And so from this data, I would like to visualize the trajectory. So pay attention here, we have several data that we have to concern. First is the azimuth and the inclination. This data we are not going to visualize, okay? Because because in its original format, the data is not complete as this. I have already prepared this data for you. So I've already calculated using the using using the trajectory calculation. I calculated all this the coordinates. So it's been available for you. So originally you have only azimuth and inclination, and you have to calculate from using minimum curvature method. I think you have already heard the term, the minimum curvature method to calculate this coordinates. And there are only three data that we visualize from this data. Only the depth. This is the true vertical depth. This is the x-axis. This is the y-axis, north-south, the y-axis, and then the east-west is our x-axis. Okay, and then the TVD will be our z-axis. Why we are not going to use this measure depth? Why? I think you have already got the answer, because measure depth is not a true depth. If when someone is going to drill into formation, they are measuring the measured depth. It is not a true vertical depth. So you have to convert the measured depth to a true vertical depth. So in the z-axis, you will define the true vertical depth. Okay, and maybe you will ask when MD equals TVD. Okay, MD equals TVD when the well is vertical. But when the well is not vertical, it's deviated well or it's horizontal, the measured depth won't equal to TVD. Okay, so we continue our discussion here. We visualize our data. So we have already had the data. So first of all, we define the data. First, trajectory df, surf, east-west, values, y, trajectory df, surf, ms, dot values, and z is the trajectory df TVD, okay, values. Okay, plot the trajectory. We have already defined the variables. Then, instead of using Matplotlib to visualize a trajectory, I would like to show you how to use a Plotly. Plotly is a visualization library. It's another visualization library instead of using Matplotlib, because Plotly is offering us how to plot in an interactive way. So I'm going to use Plotly now. Okay, so first, use this figure px figure. So okay, first we are going back to our very first here. So I forgot to import the Plotly Express as px. Okay. So this is our library for visualization of trajectory. So first, figure px dot. The function that we will use here is called the scatter 3D. Okay, the scatter 3D, and okay. So the first input is the data frame, because here the name of our data frame is trajectory data frame. So first, trajectory data frame. The second input is the x value. Okay, the x value is the column here. Okay, so x equals this one, and then the y-axis is this one. And the third input is the TVD. Okay. All right. Okay. So and then we show the trajectory, and it's still run. We have to wait for a couple of seconds. So voila, we have already obtained the result here. This is our trajectory, but it is not so beautiful. I can make a color here. So what is the difference between using Matplotlib and Plotly? Here, if we are using Matplotlib, we cannot be interactive with our plot. We can rotate this plot. Okay, so we can rotate this plot. We can hover this. We can track this line. You can see all of the information here. Okay. So Plotly is a really cool library to visualize our data because it's interactive. If we are using Matplotlib, we cannot do this thing. Okay. And one thing, again, we observe that the depth is not increasing from the shallower to deeper. Okay, so it should be from 500 to 3000 at the bottom. Okay, so we have to again reverse the z-axis. How to reverse the z-axis? So we use the figure update dot scene. Then z-axis, auto range reversed. Okay, so it will reverse our plot. Okay, so you notice now we have from 500 to 3000 at the bottom. Okay, this been already reversed. Okay, and then I would like to make a color for every points here. So I would like to plot the inclination. Okay, so we use the color C equals azimuth. Color equals azimuth. So we will look at the difference here. Okay, so each point here you can see the data from the azimuth. Okay, so here actually this is really important when we make a visualization. We have to make first our plot is beautiful, so that maybe our clients or our customers or any other people can understand the data, our data, and they can have an insight from our data. So because so for example here we can understand in which section of our wellbore plan or wellbore trajectory is having the highest azimuth. or highest inclination. So instead of maybe azimuth, we can also plot the inclination. Okay. Okay, so this is the inclination from the zero, so from the lower inclination to the higher inclination. Okay, so yeah, we can zoom in and zoom out because it's quite interactive. You can track this trajectory. You can see the data, the inclination, the TVD, and everything else. Okay. Okay. So maybe is there any question about this part? I will check. Okay. So maybe so there are no questions for this well-bore trajectory visualization. So I think I'll go directly to the next part. So now we are going to discuss another new topic. I believe that maybe I guess there's still no course discussing about natural fracture analysis. And in this session is special because we are going to learn something new. We are going to visualize a natural fracture. Okay. So what is a natural fracture? Well, natural fracture is a geological evidence, or it's caused by fracturing, by tectonics, or by subduction process, or any other process related to the sedimentation and tectonics. And how to visualize or how to describe a natural fracture. Okay, if you have already, I believe you have been you have already got a geology class in your college. I believe so. So you are familiar with the terminology of strike and dip. If you are not, so I think I will share my slide. So so this one is the picture of a natural fracture. Okay, so a natural fracture is described by two measures. The first measure is the strike angle, and the second measure is the dip. The strike is basically a measure or a degree, how far the degree is from the north. Okay, so for example, the fracture is directed to the east. So you will your fracture is said to have a strike of 90 degree. Okay, so for if your fracture is directing to the south, so it will, yeah, you guess it will print you'll describe it as 180 degree to the south, to the south. Okay, and another measure is the dip. The dip is how steep a fracture is from the horizontal plane. So in this picture, this is the horizontal plane, and this is the orientation. The strike and the dip is from the end plane, and this is B. B is the dip angle. Okay, so we always characterize fracture using strike and dip. Okay. Actually, there are other measures. For example, aperture. Aperture is how it's how big an open fracture. So you can measure several millimeters or several micrometers of the fracture inside your rock. Okay, and how to visualize the strike and dip. In geology, we are using what is called as a stereonet. Okay, so in this topic, I would like to show how to visualize a natural fracture using a stereonet. So first of all, I load the data. Again, the data is in a CSV data, so we use use the pandas read CSV. Okay. Um, frac equals panda read CSV, and the fracture, because here we have already had the link, the fracture. This is the link. So fracture path. Okay, so this is our data. We have this depth, strike, dip, the dip direction, and the aperture. What is the difference between dip and dip direction? That's it's another discussion. But anyway, for this topic, we will discuss only for strike and dip. Okay, so there is also an aperture. Aperture is I said before how open a fracture. This is 4 millimeter, 5 millimeter, or 7 millimeter. So here in this data, we have these two data, the strike and dip data, okay, and also the depth, okay. So from this data, we will visualize this data using a stereonet, okay. So what is a stereonet? Stereonet, well, stereonet is it's a stereographic projection of a plane, yeah, of a plane, yeah, a stereographic projection from of a plane to a plane. So actually, that's if I think it looks like complicated. So if you are analyzing a fracture, you can imagine it like a plane. So if you project a plane into another plane, but the projection is a stereographic. So you already know lots of projections. For example, Cartesian, spherical, cylindrical projection, and we also have what is called as a stereographic projection. So in the natural fractures, we use the stereographic to visualize our data. So first, we define the strike is the frac df strike. Okay, so this is a strike, and then this is the dip. So the frac df dip dot values. Okay. Frac. So this one is without df. Okay. So to produce the stereonet, and another thing we are going to discuss what is a Rose diagram. To produce a stereonet from a natural fracture data, I have already built a function in my GitHub. So I have already imported here. The function is called the fracture. So if you see inside the fracture, as we have already done before, you will see two functions, the stereonet and the Rose diagram. So the first thing, I would like to use the function that is called the stereonet. So stereonet, and the inputs are only the strike and dip. Okay, and if you run this code, okay, so again, because we are using the library, so we have to define first what is our library. Okay, so every time we use pandas, we use pd.readcsv or numpy-array, np.array, or plt.plot. So here we have to use fracture.something. Okay, so because we want to use the stereonet function from our fracture library, so we use fracture.stereonet. Okay, if we run this code, you will see the stereonet of our fractures here. What this plot tells us, okay, so this are our fractures. The blue lines are the strikes. The black dots here are our dips. And how to read this? You have this from 0 to 45 to 90, around to the 360. So you can see here from 0 to 45 or 60 degree, you can see the highest concentration of the strikes. So the strikes is oriented in this direction. Okay, so you can describe that the fracture has an orientation from 0 to 45 degree to the east, or to or 60 degree to the east. Okay, So this is our orientation of our fractures. Okay, so if we are going back to our picture here, so A is the strike angle. So the strike angle is from 0 to 60 degrees. Okay, and the black dots here are the dips of the fracture. Okay, so how to read the dip from a stereo net? Here we have an equal distribution all the of all the dips here. So if we see here, from this to this, you can see that this line, the horizontal or the equatorial line, is divided into several equal sizes here. Okay, so from this to this is um, 90 degrees. So this is 0, 10, 0, 10, 20, 30, blah, 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 until 90, okay? And if you see here, the dots are concentrated nearer to the 90-degree side, so 0 to 90 degree. So this is maybe this is 30 degree, 50 degree, and 70 degree. And this one is the largest concentration. So it tells us that the dip of our fracture is somewhat around 80 or 90 degree. So we have here, maybe I will write down here, the strike is from 0 to 40 degree, and the dip of our fracture is around 80 and 90 degree. Okay, so only from this visualization you can tell or you can describe the fracture that you are analyzing. Okay, actually there are also other strikes here. If you see here, there are also other strikes. This one is the orientation of 180 degree. Okay, so it's completely like a parallel, okay, to the north. It's heading to the south. Okay, so yeah, so from this plot you can tell everything about you from your fracture. But also you can also visualize the strike of a fracture using what is called as a Rose diagram. Again, this is a terminology in the geology class. Rose diagram is another visualization of the strike. So if you want to find out what is the most dominant strike in our fracture, we can use the Rose diagram to visualize it. Okay, so how we use the Rose diagram here is quite simple. We use fracture that rose, and the next thing is the strike. Okay, the input is strike, and if you run this code, you will see this plot. This is the Rose diagram. So it tells us that here there are bars here, and the largest bar points to the 30 degree. Okay, so it means that our fracture is oriented closely to 30 degree. Hey, that's really that's very close to our stereo net observation. Yeah, because here, if you see here, the distributions is more concentrated to the 30 degree. The strike is 30 degree, and again, if we are visualizing the Rose diagram, we can see that the strike is also have the same value. Okay, so if you are maybe if you have a strike of 120, so the bar will be pointed to this direction. Okay, so I hope that you understand this concept. This is how we interpret the data using the SteerNet and Rose diagram. Okay, so I think that's all for today. That's all for this session. Maybe I would like to summarize all that we have already covered so far here. So for this session, we have installed another new library. So it's called the LACIO and the MPL StereoNet. LACIO is for visualizing the Velocs, and the MPL StereoNet is for visualizing the fracture data. And also we are using the plotly to plot the trajectory data. And then, so this is the functions and this is the data. And then for the Veloc data, here we are trying to find the data, the mnemonics of our data. And then we convert the data into a data frame. And then we are using the for loop to visualize all the data into subplots here. Don't forget to reverse or invert the y-axis because it must start from the shallower to the deeper depth, okay? By using the PLT y-lim from this to this, okay? And then don't forget, there is also an important thing here. This is called how to make a subplot using a for loop. So this, because we have 5 data, okay? We use 5 columns, okay? So maybe you still remember how we describe this plt.subplot. The first input is the number of rows. The second input is the number of columns, okay? And this one is where I place the plot. So for example, the MPHI is the first plot, so it will be 1, 2, 3, 4, and etc. Okay. So if we have, for example, 10 logs, so we use 1, comma 10, comma I plus 1. Okay. For 12, 1, comma 12, and for 20, 1, comma 20, or and so on. Okay. And then we visualize the trajectory. Okay, here the trajectory is visualized using Plotly. Okay, why we are using Plotly? Because it's interactive. We can zoom in and zoom out, and we can trace the trajectory, and we can also plot the colors from the data. Maybe we want to visualize the azimuth, so we can change this into azimuth. The color is azimuth. Maybe some other data, for example, the dog-leg severity. This is the term, another term in well-bore trajectory, the severity or the angle. So we can also plot this data alongside. And also don't forget to revert or invert our axis using this. So to update the scenes using this reverse format, so we'll have this, okay? And then we have done the natural fracture analysis. We obtain this data, and then we have visualized using 2 ways. First is using StereoNet, and another one is using the Rose diagram. And the most important thing is how to interpret from this data. This is the strike. The blue lines is a strike, and the black dots here are the dips. And also, I forgot to tell you that this is the heat map. So the red color tells us the most dominant orientation of the dips in our fractures. Okay, and then we can also visualize using the Rose diagram to tell us which direction is the most dominant in our fractures. Okay, so I think that's all. I'm still open for questions. If you want to ask questions for this session, you can start typing in the chat box. Okay, thank you.
Thank you, Engineer Yohanes. It was a great session, and I would like to thank you for your efforts. Actually, you have answered most of the questions during the session, but we still have 2 more. First question, how can we apply artificial intelligence to find reservoir thickness?
Yeah, actually, artificial intelligence and machine learning is a very sexy term nowadays. People always want to do something with machine learning, with artificial intelligence, neural network, or something else. I would like to say that instead of jumping into artificial intelligence and machine learning, we'd better to understand this thing from basics. Maybe for simple tasks, we don't have to use machine learning always. Okay. For example, we want to, as you said, I want to find a reservoir thickness. I think reservoir thickness doesn't really need machine learning or artificial intelligence. Why? We can use volumetric mapping, or we can use the well logging to find the pay zone, to find the pay thickness from the well log, and then to distribute it using a volumetric or any other method, for example, contouring or kriging interpolation. Okay, so I think that's enough to do some simple task using a just basic, just only basic methods we know in engineering. And when we can use our artificial intelligence and machine learning, so we use this term when we come across a really complicated problems, or a problem that maybe some other people cannot approach using a common engineering approach. So for example, I would like to characterize the lithology from the Veloc data, okay? Because as you know, that petrophysicists, they spend lots of time to interpret the data, and then they will produce the lithology classification using a certain kinds of methods in petrophysics, using near-term density plot and other plots in petrophysics. They are using this, and they can spend, for example, 1 or 2 weeks to produce this thing. But if we use the artificial intelligence and machine learning, it will cut the interpretation time. For example, in 1 hour, we can have a really we can have a result in a really short time. Actually, the discussion on machine learning and artificial intelligence is it's a lot of more interesting. I can open another session or another podcast or talk about machine learning and artificial intelligence, when we use it and when we don't use it, when we can I think what thing we can do with machine learning and what thing we cannot do with machine learning. But I want to stress that the basic understanding in engineering is the most important thing before we are jumping to machine learning and artificial intelligence to do something in our domain knowledge. I hope that
Great.
answers the question.
Yeah, great. How to put each log range on the top of the plot?
How to put each log range on top of the plot.
Yes.
Oh, okay. So I think you might refer to this plot here. This is actually the range. This is the range of the x-axis. So maybe I think you are referring to how we can constrain or how we can modify the range. For example, here for this data, gamma ray data, you would like to visualize from 0 to 200. So we can use this actually. So maybe I can add some more codes here. For example, xlim and xmax. Oh, sorry, xmin and xmax. Okay, xmin and xmax. So for this, I make a list. Okay. So pay attention here. We have 5 logs, so we have to define five range. Okay, so we are going from first, for example, from NPHI from 0 to 45%. Okay, because 45 is the highest porosity of all rocks. It's quite possible. So the xmin and xmax here for the first column is 0, and the second one is 45. And then for the Roby, for example, from 2 to 2.7, and then from gamma ray from 0 to 200, and then for the resistivity from 0 to 100. Okay, so because the semi-log plot cannot plot in the 0, because it so 0.001 will be correct, and this one is 100. And then the range for the compressional data, compressional sonic log, is from 50 to 150. So from 50 to 150. So we have already obtained this list. So we just type this plt.xlim, okay? And again, because we are working with the for loop, so we again use the I. So the x limit is from the xmin I and the xmax I, okay? And if you run the code, it will give you the new range of data here, okay? So you will see this from 0 to 0.45, and then this one from 2. So, so you can modify this range by making this list for each log, the minimum and the maximum limit of your x-axis, okay?
Okay, the last question. Is it possible to predict the fracture distribution for carbonate reservoir using Python?
That's I think to predict fracture distribution for carbonate reservoir using Python, um, we have to go back to the basic concept of what is the carbonate reservoir. So if you still remember the difference between carbonate reservoir and the sandstone reservoir, or people call it as the siliciclastic reservoir, there is a major difference. For sandstone reservoir, you will see that the porosity is uniform, okay? So you will see only granular porosity. But in carbonate, you will have lots of different kinds of porosity. For example, foggy porosity, moldic porosity, or fracture porosity and secondary porosity, primary porosity, and dual porosity. There are lots of porosity types in carbonate formation, and this is the use of I think the use of modern interpretation to distribute the fracture inside the carbonate reservoir. And I would like to say, because I was working with carbonate reservoir several years ago, and it was quite complicated because carbonate reservoir is very different from the sandstone reservoir. The fracture behavior is really different. Um, the you can have two kinds of porosity in one reservoir. For example, the vagi porosity with moldic porosity in just one reservoir. So it's quite complicated to characterize the fractures in our reservoir. But yeah, I think you can use, for example, the methods that you know in petrophysics. There are methods in how to characterize the dual porosity or triple porosity, and then you can code or you can make a program using Python. So yeah, I think it's possible. And I would like to say that every time people ask me, is it possible to do this with Python? Is it possible to characterize something? Or is it possible to achieve this result using Python? I would say yes, because you can do anything with Python, and you can solve any problem with Python. The only thing that you have to do and you have to have is the urge to have a creativity. So creativity makes lots of interesting things. You can make even what people don't realize it before, and what people don't make it before, you can make it yourself. Okay, so I think all things are really possible in Python. You can do anything with Python, and not only Python, but also any programming language. For example, MATLAB or C++ or any programming language that you prefer. You can make all things with programming language, because I think programming language is more preferable than spreadsheet. If we are working with Excel spreadsheet, it is quite limited. We are working with tables that is immutable. We cannot modify, we cannot easily make our own program. But if we know how to program something, we can translate our problem into codes, and then from codes into another new program. So I think all things are possible in Python, and yes, characterize fracture in a carbonate reservoir using Python. Yeah.
That's all for today. Thank you, Engineer Johannes, and thank you all. The session will be uploaded to Biopetri YouTube channel, and don't forget to solve the quiz on Google Classroom. Best of luck, and thank you again.